For anything at all to happen in the universe, a force must act. For anything at all to happen in the universe, a force must act. We usually think of forces as moving things around, pulling this apple towards the ground or pushing a car up a hill. But forces also cause the sun to shine. They make the ice melt in your drink, and they cause a plant to emerge from a seed. Forces are the agents of change in the universe. To help us understand forces, thousands of scientists around the world have spent billions of pounds to build this machine. I'm standing 100 metres below the ground at CERN in Geneva, and this is the CMS detector, part of the largest and most complicated scientific experiment ever attempted. This experiment will give us deeper insight into the forces of nature than ever before. It's a long way from when Isaac Newton pondered the laws of gravity, but all part of the same story. We understand the world today in terms of four forces of nature: the strong and weak nuclear forces, electromagnetism and gravity. Now, gravity is perhaps the most familiar, but in fact it's by far the weakest of the four forces. So weak, in fact, that we can completely ignore its effects when we explore the subatomic world, at least with today's experiments. Besides the familiar but weak force of gravity, there are three other forces in this universe, each of which is vital for our existence. Now, it may not seem obvious, but the force that holds these bubbles together is the same force that allows this flame to burn. Electromagnetism. It's the force that allows us to push and pull things, the force that allows us to see everything in the world around us, and the force that allows your TV set to work. Electromagnetism is the force that holds electrons in place around the atomic nucleus and holds the atoms and molecules in place in my body. It also causes electrons to repel each other. So even though the whole planet Earth is pulling the apple down to the ground, the apple stays firmly in my hand because the electrons in its surface are repelled by the electrons in my palm. I've used the word electromagnetism to describe a single force, but electricity and magnetism seem at first sight to be very different phenomena. The magnetism that makes this top levitate seems to have nothing in common with these electrical sparks. The Greeks knew that if you rubbed a piece of amber with fur, it would pick up feathers. They also knew that certain rocks attracted iron, but they had no idea that the two were related. For 2,000 years after the Greeks, we thought of electricity and magnetism as different phenomena. It wasn't until the 19th century that we discovered that they are, in fact, different manifestations of the same thing. Now, not a lot of people know this, but this silver box inside a traffic island in South London is in fact a monument to the man who set us on the road to that profound discovery, Michael Faraday. Inside here is an electrical substation that powers the Elephant and Castle tube station across the road. Now, the original idea was for this to be made of glass, so you could see the electrical transformers inside. And I think that would have been an even more fitting tribute to the genius that was Michael Faraday, because it's really true to say he was the founding father of the modern electrical world. Well, this is a more obvious monument to Michael Faraday outside the Institution of Engineering and Technology. And in here, they have some of Faraday's original notebooks. In this notebook, in Faraday's own elegant, if rather illegible handwriting, is a reference to his most famous discovery. It's here in the title, Convert Magnetism into Electricity. What Faraday had found is if you take a coil of wire and you move a magnet around inside it, you generate electricity. And it's machines like this that lie at the heart of every power station in the world. Faraday had shown that electricity and magnetism are intimately connected, but they weren't yet unified together into a single mathematical framework. It took a very different kind of physicist, James Clerk Maxwell, to see the true connection, and with it produce a revolution in our understanding of the universe that Einstein later described as the most profound and the most fruitful that physics has experienced since the time of Newton. This is the lecture theatre where Maxwell stood and taught electricity and magnetism to his students. I want to show you something about the beauty and predictive power of mathematics in the hands of Maxwell. These are almost Maxwell's equations. They predict everything that was measured by Faraday and his colleagues about electricity and magnetism throughout the 19th century. This, for example, is Faraday's law of electromagnetic induction. But Maxwell noticed that these equations are not mathematically consistent. He was forced to add an extra term, which is called Maxwell's displacement current. With this extra term, these equations can be recast into this form. These equations are equations for electromagnetic waves, waves of light. So, in one piece of genius, Maxwell had unified the forces of electricity and magnetism and made a profound connection between electromagnetism and light itself.
Maxwell's unification of electricity and magnetism is regarded as a great milestone in physics because it was the first time when two disparate pieces of physics, electricity and magnetism, both thought of as separate physical processes, were brought together under a single theory which incorporated the two together. And that's a very important thing in physics, to try and explain as much as you can as simply as possible.
The two forces of gravity and electromagnetism seem at first sight to be sufficient to explain everything we see or feel in our everyday world. But once we look inside the atom, it is immediately obvious that other forces must be at work in the universe.
By the mid-1930s, we knew that atoms are composed of electrons orbiting a nucleus of protons and neutrons. But there's a problem with this model because protons are positively charged. And so when they're close together, the electromagnetic repulsion should blow the nucleus apart. And that's not what happens, of course. There must be another force many times stronger than electromagnetism that glues the nucleus together. And that force is called the strong force.
The strong force is not only responsible for holding the nuclei of atoms together, and without that, every atom in the universe would just spontaneously explode. But it's also, and this is quite interesting, responsible for 98% of nuclear mass. That means 98% of my mass, your mass, the mass of the sun, the mass of the earth. And we don't quite know exactly how the strong force generates that mass. And so we want to study that in more detail.
The discovery of the strong force was a giant leap forward in our understanding of nature. But there were still phenomena that we couldn't explain. This is a PET scanner, and it's transformed the way we diagnose many diseases because it allows us to look inside the body and detect abnormalities in cellular activity. Machines like this were developed as a direct result of advances in particle physics. The P in PET stands for positron, an antimatter electron, identical in every way except it has opposite charge.
Positrons or electrons are emitted from the nucleus in radioactive beta decay.
And that's a process that baffled physicists throughout the early 1930s. And they knew that the nucleus was made up of protons and neutrons held together by the strong force. And they knew that beta radiation came out of the nucleus. They also knew that beta radiation was comprised of electrons. So where did the electrons come from? It was the Italian giant of science, Enrico Fermi, who finally solved the problem. In 1934, he proposed that there's a weak nuclear force that can convert protons into neutrons or neutrons into protons, at the same time emitting electrons or positrons and neutrinos from the nucleus. Fermi had found the missing force that explained the inner workings of the atom.
He played a huge role in nuclear physics, and his weak force has played a huge role in us being here. In fact, it's critical that it's so weak because it controls the first stage of the sun's fusion cycle. Because it's weak, the sun only just keeps alight. It's been burning for 5 billion years already. If the weak force had been any more powerful, the sun would have burnt out before any of us got here.
Fermi's discovery of the weak force is not the end of the story. A few decades later, in the 1960s, scientists were able to bring together the weak force and electromagnetism into a single electro-weak force.
Is it possible that the strong force, and perhaps even gravity, could be unified with the electroweak force into a single superforce that ruled the universe in the first instant after the beginnings of time? Well, Maxwell's unification was inspired by experiments done on a single desktop. The experiments that may lead to the long yearned for theory of everything will be controlled from here, the nerve centre of the accelerator complex at CERN. Here, we'll recreate the conditions that were present in the universe less than a billionth of a second after the Big Bang. How do we recreate those extreme conditions here on Earth? You need one of these, the Large Hadron Collider. 27 kilometres in circumference. Inside here, we accelerate protons to 99.999999% the speed of light before bringing them into collision inside 4 giant detectors. And those detectors take pictures of the collisions 600 million times a second. These are the lengths we have to go to explore the forces of nature. Today we can describe everything that happens in terms of just 3 forces: the electroweak force, the strong force, and gravity. But some scientists dream of going even further and unifying those forces together into a single force, a theory of everything. Imagine a world where things can pop into existence seemingly out of nothing and disappear just as quickly. Imagine a world where you can be everywhere in the universe at the same time, and yet nobody can know precisely where you are. According to our best theory of nature, the standard model of particle physics, this is exactly how the world behaves, because at its heart lies the strange theory of quantum mechanics.
Quantum mechanics took away all the certainty that classical mechanics had put into nature. In the classical world, everything goes like clockwork. If you know where everything starts and how it's moving, you can predict where everything's going to end up. Quantum mechanics has this concept of uncertainty built in.
We can't know anything with absolute certainty. We can only work out probabilities of different outcomes happening. We have a very hazy view of matter because quantum mechanics tells us that matter doesn't just consist of particles. Particles can also behave as waves. And it's a very confusing and non-intuitive way of looking at the universe, something that we're not really used to at all.
Now, quantum mechanics at first sight seems like a pretty strange view of the world, but it's experiments like this, the photoelectric effect, done at the turn of the 20th century, that forced us into that picture. Now, this is a gold leaf electroscope, and it's charged up. There's an excess of electrons on this plate, which causes the gold leaf to rise. Now, watch what happens when I turn a light on. The light forces the electrons off the plate, discharging it, and the leaf falls back down again. Now, that's pretty easy to understand. What isn't is that the energy of the electrons that come off the plate depends not on the brightness of the light, but only of the colour. Now, that is impossible to understand if you think of light as a wave motion, and it took Albert Einstein to come up with the correct explanation. He said that you can picture light as a stream of particles called photons, and not as a wave. And the energy of each photon depends only on the colour. That realisation, that explanation of the photoelectric effect, lies at the heart and at the foundation of quantum theory.
Einstein's explanation of the photoelectric effect presented a new challenge to scientists. Up until this time, they had explained the properties of light in terms of waves. Suddenly, it seemed that light could also behave like particles. How could this be?
The resolution to this seeming paradox had to wait for three of the giants of 20th century physics, Feynman, Schwinger and Tominaga. Working independently throughout the 1940s, they discovered a quantum theory of light, quantum electrodynamics, or QED.
Where Einstein had explained the photoelectric effect in terms of particles, Feynman and his contemporaries went even further. With quantum electrodynamics, they provided a mathematical way to explain all the wave behaviour of light in terms of particles. QED was a major milestone in our understanding of nature.
I think Feynman referred to QED as the jewel of physics. Probably not because he invented it, but it explains all of physics outside the nucleus and excepting gravity. Okay, so it is a theory that explains the interactions of matter particles with one another via the electromagnetic force, and that drives all of physics and chemistry and material science. And so it's a theory of almost everything.
As well as explaining the behaviour of light, QED provided a revolutionary way to look at forces. Instead of thinking in terms of force fields, as Newton and Maxwell had done, QED explained the electromagnetic force in terms of particles. To understand how it works, imagine two electrons approaching each other. We know that they'll move apart because like charges repel. QED says that the repulsion is caused by a photon, a particle of light, being transferred between the two electrons. So the photon is the particle that carries the electromagnetic force.
QED proved so successful that it seemed natural to look for quantum theories of the other forces that concern us as particle physicists, the weak and strong nuclear forces. By the mid-1970s, theorists had predicted that the strong force required 8 exchange particles called gluons, and the weak force required 3, the W+, the W-, and the Z. The problem was that these were just mathematical predictions, and as with everything else in science, if you want to be really sure about something, you have to see it. And to see it, you need one of these, a particle accelerator.
Scientists have been building particle accelerators since the late 1920s. As well as letting us look at the structure of matter, they allow us to create hitherto unseen particles that our theories tell us should exist, like the elusive gluon. The secret to creating new particles lies in the most famous equation in science, E equals mc squared. What this equation means is that mass and energy are interchangeable. Particle accelerators make use of this. They speed particles up and smash them together. The energy from the collision can turn into new particles. It was in 1979, when particle physicists still wore flares, that a brand new particle detector called Petra revealed the first spectacular evidence for a force-carrying particle besides the photon. The detector produced results like this, which could only be explained by the particle that carries the strong force, the gluon.
The W and Z particles took rather longer to find. That's because they were predicted to be extremely massive, and we know from Einstein's E equals mc squared that it takes a lot of energy to make a lot of mass. So it took the biggest particle accelerator of its day, the SPS, and the most sophisticated detector of its time, this UA1, to coax them out into the open. But eventually they were found, force-carrying particles like the photon and the gluon, but with more mass than a nucleus of copper. The discovery of the W and Z particles was a triumph for particle physicists, because they now had a complete set of the force-carrying particles. But that's a long way from the end of the story.
Why are the W and Z particles so massive when the photon and gluon are mass-less? The maths just doesn't add up as elegantly as we'd like, and we suspect there's a missing piece of the puzzle.
In the early 60s, British physicist Peter Higgs came up with a way of generating masses for the particles that, quite magically, avoided the mathematical difficulties. Now, the Higgs mechanism is quite a complicated bit of physics, but we've had over 40 years to come up with good analogies, and here's one of the best.
These are physics students. They represent the Higgs particles, filling every corner of the universe. If a popular lecturer like Fred walks through the students, they crowd around to ask profound and intelligent questions, and his path across the grass is slowed down. He has acquired mass.
But if a less popular lecturer walks across the grass, then everyone ignores me. I'm a massless particle like a photon, and I can travel through the universe unimpeded at the speed of light. We don't know if the Higgs particle exists or not, but to find out, scientists have built the biggest particle accelerator ever. I'm standing 100 metres below the ground at CERN in Geneva, and this is the CMS detector, part of the largest and most complicated scientific experiment ever attempted. Here, we'll recreate the conditions that were present in the universe less than a billionth of a second after the Big Bang. How do we recreate those extreme conditions here on Earth? Well, you need one of these, the Large Hadron Collider. 27 kilometres in circumference and filled with over 2,000 superconducting magnets, each at 1.9 Kelvin. That means that they're colder than the space between the stars. Inside here, we accelerate protons to 99.999999% the speed of light before bringing them into collision inside 4 giant detectors.
The LHC is going to be exploring totally unknown territory, but that doesn't mean to say we have not got some ideas of what might be there. And one of the most famous examples is the idea of the Higgs boson. And this, according to theory, is a manifestation of what happened when the universe froze. Now, I don't mean froze like at ice temperatures, I'm talking about 10 with 17 zeros after it degrees. That before that time, according to our best theories, the universe was in a state of beautiful symmetry, whereas today it's full of structure. And just as the structure of the snowflake emerges when water freezes, so in our theories the structure of what we call the standard model of particles and forces emerges when the universe froze at this incredibly high temperature.
Why would we build all this to understand the universe? The universe today seems almost impossibly complex, full of planets, stars, and even life itself. But over centuries of experimentation, we found that the complexity is really a property of an old, cold universe. When the universe was much younger and much hotter, it appeared to be much simpler. And so it's here that we're going to recreate the conditions that were present in the very earliest times to hopefully reveal that underlying simplicity.
Well, speaking as a cosmologist, the LHC will be exciting because it should say yes or no to whether the Higgs boson, a type of particle, exists or not. And it's a sort of particle that cosmologists are interested in because we think particles of that type are responsible for a very rapid expansion of the universe in its early history, which forms the cornerstone of modern cosmology. It's a theory called inflation.
The standard model, our theory of particle physics that we have, tells us that there should be a Higgs and we should find it without trouble at the LHC. But our theory could be wrong. We know that our theory is incomplete, which means it has to break down somewhere. So if we don't find a Higgs at the LHC, it could be a sign that a new, deeper, underlying theory of matter is just about to surface.
When you go to a new regime like the LHC will, quite often something pops up that's unexpected and can take physics down a different path altogether. And that's the sort of exciting physics that I'd like to see at the LHC.
Well, the LHC could find that there turn out to be more than 3 dimensions of space and 1 of time, and particles can actually disappear into extra dimensions, which is pretty wild and wacky, but it could be real science and not science fiction at the LHC.
I wouldn't like to predict what will happen at the LHC. It's like guessing what we'll find on our first journey to the stars. But the giants of history would have loved access to this machine because science is about exploring, and the only way to uncover the secrets of the universe is to go and look.